Hello, folks, and welcome to the third episode of ZK for Impatient. Today, we're going to start discussing how ZK can be used to build a machine that runs real software, something that people in blockchain industry call a ZK-EVM. But before we start, let's do a quick recap of episode 2. As you remember, in episode 2, we learned that ZK turns every mathematical computation or formula into a sequence of additions and multiplications. This is something that ZK calls addition and multiplication gates. And then, in turn, these gates can be injected with a hidden ZK law that can be verified. That's something that we learned the last time. Our today's subject is ZK-EVM. ZK-EVM is basically a verifiable computer running in ZK, or something that computer scientists call a Turing machine. In 1936, Alan Turing, one of the founders of computer science, came up with a definition of an abstract computer. A computer is a device that does four things. First, it reads some items from memory. Second, it does a computation on these items. Third, it writes results to memory. And fourth, goes to step 1 in a loop. ZK-EVM is just a verifiable Turing machine. We already know from the previous episode how to create ZK proofs for computation, which is step 2 of Turing machine. And today we're going to discuss verifiable memory, which corresponds to step 1 and step 3. Let's start with a simple example. There is a king and a librarian, and the king wants the librarian to read a particular sentence from the Bible, line 1 of page 2. The librarian reads the sentence, but the king also wants a proof that the sentence is correct. This is what we call verifiable memory, not only providing information, but also providing proof of this information. Turns out that verifiable memory is actually possible due to an algorithm designed by Ralph Merkle, a computer scientist from UC Berkeley. And we are going to discuss a simplified version of this algorithm. Here we have a sentence from the Bible, and we want to store the sentence in a verifiable way. What we're gonna do is build a so-called Merkle tree for this sentence. First, we replace every character in the sentence, including space characters, with the corresponding number. You know that computers encode characters into numbers using something called ASCII encoding. So this is how we get to bottom line of numbers. And then what we do is add up each pair of numbers, divide the result by 13, and then take the remainder of division. For example, the first pair is 6 and 11, so we add these 2 to get 17, and then if you divide 17 by 13, you get 4 as the remainder, which is the top element here. So that's how we get the next line, and we keep on building the tree until we end up with the top element, which we call Merkle root. In this particular example, the Merkle root is 7. As an exercise for you folks, you can check this tree and verify that each parent element is obtained by first adding the left and the right child, and then getting a remainder of division by 13. Okay, now how do we build a proof that a particular letter belongs to the sentence. Let's build a proof that the fourth letter, letter S, belongs to the sentence. First, we find this letter in the tree. Its numerical representation is 10. Then, to build the Merkle proof, we start with 10, go up the tree, and each time take the sibling of the element. Then all of the elements of the Merkle proof are marked in blue, and the final element of the proof is always the top element or the Merkle root. Now let's see how the verification algorithm works. The librarian stores the sentence in memory. The only thing that the king needs is to know the Merkle root, which in this case is 7. And then basically the king asks what's letter 4 of the sentence. And the librarian responds that it's S or 10 in numerical representation. But then the librarian also sends back the Merkle proof, which, as we know, are all of the siblings on the way from 10 to the top of the tree. Now, what's important is that to verify things, the king takes every pair and verifies the division by 13 law. For instance, that 3 plus 10 is 13, and the remainder of the division by 13 is 0. So the bottom three numbers are correct, 3, 10, and 0. And then basically the king verifies all of these three number combinations. And then as an exercise, you folks can verify this entire proof and also build Merkle proof for other letters in the sentence, just to get a better feeling of how the Merkle algorithm works. Now, a Merkle tree that simply uses division by 13, as in our example, is really not strongly secure. And in the following episodes of our series, we're going to discuss more algorithms for the Merkle tree. Algorithms that even a computer can't break. But for now, this concludes our intro into ZK verifiable memory and Merkle trees. And the last subject, let's discuss how real-life ZK works on SKALE-ZK. In our case, in case of Scale, ETH mainnet plays the role of the king that verifies things, and the ZK chain from Scale, a SKALE-ZK chain, plays the role of the librarian. So for each block that is built on SKALE-ZK, what is submitted to the ETH mainnet is the Merkle root of Scale chain, of the entire information on Scale chain, including, for instance, funds and accounts and money, just before block processing. Then we also submit the new committed block, the new block, and the Merkle proof of the chain information after block processing. Finally, we submit the ZK proof for all of these items, all of the items above. So then ETH mainnet uses the ZK proof to verify all of these elements. And once the verification happens, users can trust the new Merkle root and use this Merkle root to verify pretty much any information about Scale chain. For instance, how much money a particular account has. So that's pretty much anything. You can verify anything. Well, congratulations. We got to the end of today's episode. And the next episode is going to discuss secure ZK algorithms, and a particular algorithm which we'll use a lot at Scale, the algorithm which is called Plonk. For today, thank you, folks, and please stay tuned for next episodes. Thank you.